Bonjour tout le monde. Donc, aujourd'hui, nous accueillons le professeur Essam Mansour, qui nous vient d'une université montréalaise, l'Université de Concordia. Donc, il est professeur à l'Université de Concordia et directeur du laboratoire en Cognitive Data Science. Donc, il est lié aux sciences cognitives à travers ses recherches. Et il nous présente aujourd'hui une thématique liée au machine learning, je suppose, federated machine learning. Et le titre de sa présentation est Towards Cognitive Data Science Platforms, Challenges and Opportunities. So go ahead, Professor.
Thank you very much for the invitation. I'm very happy to present the work we are doing in our lab codes with the seminar here. And actually, you are focusing, as it was mentioned, on cognitive data science. Today, I'm going to speak more about the challenges and opportunities. And first of all, my name is Essam Mansour, and recently, like in 2 years, I joined Concordia. Right now, I'm focusing on cognitive data science. Mainly, we are using NLP techniques and deep learning on knowledge graphs in order to make data science platforms smarter. Before that, I used to work with different topics related to elastic database systems, data discovery, and mobile data management. Just to give a brief idea of where I used to publish my work, I mainly like database system conferences, and most of my publication is published in VLDB, Sigmod, ICDE, these kind of conferences. Okay, now, what do we mean actually by cognitive data science? So let's start one step back. What do we mean by data science? Nowadays, like there is a lot of data initiatives in order to make data public. You see that with governments. We see that with even big organizations, where we are trying to have transparency by making data public and easy to access. We see that in Quebec, we have Quebec data portals, and this is actually providing a lot of information to related application domains. We see that with Kaggle. So in Kaggle, we do not only have data, we have also what we call it data science pipelines. So we have some initiatives of actually providing how we can analyze this data in order to get insights. So we have, this is now available to us. Now there is initiatives now in order to make the community in general, like scientists benefiting from each other, not only data, but also their investigation about this data. And just to give an idea, if someone maybe not aware of what is a data science pipeline is, you can expect something like a data set, and then you start writing code. As you see here, we are saying this is data plus code, where you have, like in your script, you'll be loading this data and start doing some of data preparation. Sometimes you need to do transformations, you need to do cleaning. This is what we consider as data preparation. And then you start maybe training models on that. The thing that, although data science platform is helping you to do this kind of pipeline, but it is not intelligent. Like they are relying on the data scientist or the data engineer or software developer in order to do everything on their own, discovering data, which is very time consuming, predicting what kind of models you should use for these data sets. And this is why we now thinking, okay, why not also automating this process? So right now, what we have, Kaggle or OpenML or open data portals like the federal government of Canada or Quebec, they actually have some tags, some keywords describing the data set available. Or even in Kaggle, they have also some metadata like tags or something for the script that has been loaded for a certain data set. And this is very, very limited way to search this valuable information, okay? And this is why we are actually spending too much time in order to find data sets and joining this data set together. just to give you a brief idea of how big this data set is. For example, in Quebec Data Portal, we have more than 1,200 data sets. We are speaking about data sets that is regularly, like per month, they are updated by adding new data sets or updated by changing loaded data set before, like the existing data sets. Enterprises, like nowadays in Canada, all big banks, they have their own data science labs. And these data science labs, they like Borealis AI, we have collaboration with them. They actually accessing huge amount of data. Not only data, but also their own, data science pipelines they, invented for analyzing and getting insights from these data sets. So this is like, for another example here, the federal government of Canada, they have more than 80,000 data sets. Kaggle itself, they have thousands of data sets and hundreds of thousands of machine learning pipelines. Why I'm referring to all this huge amount of data that is available right now? Because if you would like to make data science platforms smarter, meaning you would like to automate some of the stages in these pipelines. And in order to automate that, meaning building models, you need a kind of data. And the data is available, but it is available in a way that is hard to consume, that is hard to investigate. So as we see here, it is hard to search like this kind of data portals. Now, our objective is not just to search. The objective that we are trying to achieve in our lab is actually having automation for learning automation. Like automatically, we are learning from what is happening. Just imagine for COVID-19, how many data sets has been produced over these 2 years? Not only data sets, how many pipelines, data science pipelines for investigating these data sets in different sectors. Like COVID affected different sectors, affected our economy, affected transportation, affected a lot of sectors. So if I would like to start from something like that, I don't want as a data scientist to start from scratch every time I got a new data set. Imagine now this running example here, we have lab 3. Lab 3 has a scientist who's interested in a certain task to analyze. And for this a certain task, maybe there is some relevant data sets. So that data scientist just dreaming, how can I just find the most recent, insights related to a certain data set? Even more, how can I find, or not starting from scratch, writing this machine learning pipeline, but directly, if the system is learning about what is going on, I can directly, give insights or help, the data scientists in lab 3 to do all this kind of discovery for relevant data, or this kind of discovery of what is the most, appropriate modeling technique or classifier to use in order to analyze a certain data set. Right now, existing data science platforms, they are lacking this kind of functionality. Although we are trying to build smart systems using deep learning and NLP techniques and all this kind of stuff, but the pipeline itself, in order to create this kind of insights, is not smart. We need to make it cognitive data science. And this is now, what do we need in order to reach that thing about cognitive data science? So here, imagine that in this figure, this is just a very conceptual abstraction of what is going on. Usually, when you look at data portals here, something like open data portals of federal governments like Canada, US, over Europe, or Quebec, usually this data originally stored as, raw files like CSV files, JSON documents. So there is no way, actually, there is no global schema that you can use in order to automatically search and navigate these available data sets. So imagine somehow we are going to build a knowledge graph or a graph for now, which is actually abstracting the information or the semantics of the data sets. Now, we are not talking about the raw data. We are talking about semantics that is going to be extracted from these data sets in order to know, oh, this data set is speaking about a certain topic, and this is a kind of connections between data items in these data sets at very conceptual level. Now, these data sets will be consumed in a certain data science pipeline. So where we have code that is trying to read these data sets and analyze it. Now we start analyzing the script. Now we are not going to deal also with the raw script, like the Python script. We would like to extract semantics, like abstracting the pipeline in order to be kind of this kind of operations that you apply on certain data set. So this is the challenge now. So we are trying to decouple the semantics of machine learning pipelines, the semantic of data, from the actual system that is consuming these pipelines or using this data. And in order to do that, we are working now. We already have a prototype of that system. We call it KG LEDs. LEDs for linked data science. So what actually we are trying to do? We are trying to do different ways of data profiling. So you get access to certain data sets. You try to do different kind of data profiling in order to extract semantics about this data. And also we do also pipeline abstraction. Pipeline abstraction, it means instead of dealing with the raw script that you are writing for your data science pipeline, we would like to abstract it in a kind of a knowledge graph where we are focusing on the semantics that you are applying in order to generate insights from a certain data set. Once we have that knowledge graph, we can automate a lot of stuff. Like we can learn what now we have hundreds of thousands in Kaggle, for example, of data science pipeline that is written for a specific data set. There is something we need to consider here. These data science pipelines are generated by human, and usually when someone uploading their own data science, they are uploading something that is actually achieving very high accuracy. So if we manage to get this abstraction of semantics from data and pipelines, now we can learn, we can automate models to do data preparation. How can we do that? Now, the things that we are relying on for similar data sets, we can see that this is something we managed to observe. We can see in Kaggle, for example, for similar data sets, we are doing similar kind of analysis or building similar kind of models. For example, you can learn for similar column or data if it is non-numerical. Usually data scientists, they try to transfer this data to a kind of numerical values or normalizing the data in a certain way. Now we can learn this kind of stuff to do automatic data preparation. We can also do what we call it AutoML, which is actually predicting a classifier or predicting transformation for a certain data set. This is a well-known area. And also we have now, we have the state of the art right now in order for solving this problem based on this kind of, converting or redefining again pipeline automation as a graph generation problem. Now we can learn from the knowledge graph how we can predict a certain complete pipeline for similar data sets. Another project also we can do on top of that, feature discovery. And feature discovery here, if you are training machine learning models, you can actually predict a set of features based on similarity between data sets. This is now like our system. We have now a project with Borealis AI. This is one of the AI labs for RBC Bank. And we are trying to customize our system for the discovery in order to do that for them. Okay, how we can do that? So first of all, from our investigation about abstracting semantics from data sets first I speak about data. There is these traditional ways of data profiling. And could be like, for example, if you have, we are speaking more here because this is what you can see in most of the open data portals or Kaggle. We are speaking about structured data, meaning you have like CSV files or JSON documents. Now, there is a lot of techniques in order to analyze this data by statistics, like getting like some statistics about these columns, what is the minimum value, what is the maximum value, this kind of stuff. However, false positives in order to correlate between similar data items is very high. So what we have been working with, and we are getting very good results here, we built our own deep representation learning models from data sets. So we are trying to learn, and generating embeddings for data sets, for a certain table, for a certain column. And the good thing about that, we can correlate based on these similar columns based on the embedding we are generating. There is a lot of advantage here, like we are getting better accuracy of correlating between similar data items, comparing with the traditional techniques. Now, in order to abstract pipelines, usually there is two techniques. Like if you would like to convert a certain code or script into a graph. So you can use dynamic code analysis in order to do that. But the thing that dynamic code analysis is very expensive because you are required to run the code and preparing the environment for running this code, which is very challenging. The other technique in the opposite side is a static code analysis. In static code analysis, you don't need to run the code. You just go through the script as it is called static analysis. However, this is very, very limited in discovering things. So in order to solve this scalability issue, we actually invented a mechanism that is relying on a static code analysis, but not only that, because there is some stuff that we cannot discover by just looking at the code. So we are relying also in analyzing documentation of libraries. We are here focusing more in Python libraries, and this documentation of these Python libraries are available. One of the examples here, like if I would like to predict for a certain variable in this code, what is the output of this function? The static code analysis will not give us a way to do that. By analyzing the documentation of the libraries, we can predict the output of this function code. And with that, we end with a graph pair pipeline, and then we connect this graphs, which is actually an abstraction of a certain pipeline, with the data that is consumed within these pipelines. So as you see here in the top, the blue nodes is actually data sets. So, but this is the semantic of these data sets. And then it is connected, and this is what our system is doing. We are figuring out the connections, how these data sets has been consumed in different pipelines. And what you see here in red is actually Python libraries that has been used in different pipelines. Now, the good thing, if you can look at that knowledge graph, is actually a semantic of all data items you have and all kind of libraries we are using in order to build pipelines, writing a script to analyze and get insights. Now, on top of that graph, we can automate a lot of stuff as we are going to see now. Now, when we compare, like in order to find a baseline to compare with, to the best of my knowledge, we are the first to come up with this system to construct a knowledge graph for data science projects. However, you can look at that graph or this system as part of it. There is a similarity between this and data discovery. So there is indeed some systems doing data discovery over data lakes. Two examples here of these systems, a system called D3L, and this was published in 2020 at ICDE conference. ICDE conference is one of the top tier conferences in data systems. AROM was published 2018 in the same conference also. And as you see here, now the x-axis is actually varying number of keys, like the things that you are looking for. And y-axis is the precision in the figure in the left and recall in the figure to the right. And as we see that our KG-led system is really doing much better, and this is like the main reason here for better discovery. This is relying to our technique of deep representation learning from this, and this is actually helping us a lot in reducing, false positives. And one of the things here, like we recognize existing systems, for example, they get confused a lot with numerical values. However, using our technique, we can really correlate much better in terms of the semantics or based on the representation learning we had on top of this data. Okay, so we end with constructing the graph. There is also existing systems, and this system we are comparing with was developed by IBM Group. Right now, we are actually collaborating with them for solving the problem of AutoML problem. And in this close collaboration, we managed to show them that, if we use your system, which is generic for code, not specifically for a script, Python script that is written for data science, we need to focus on some aspects, not general as code. And here in that table, we are showing you that now, in order, for example, after building the knowledge graph, here we managed to build for 2,000 Kaggle scripts, Kaggle pipelines. In terms of the graph itself, we are about 97, less in terms of the graph size. So we managed to have like about 97 reduction in the graph size comparing with the IBM system. And this is actually leading to less number of nodes and less number of edges. Now, when we train models on that, due to the very noisy graph generated by the IBM system, they are consuming more time. Like as you see here, they are consuming more than 175 minutes in order to train models on such a graph. Now, we are training our models only in 2 minutes. And as you see that trained model, which is trained in less time to predict, transformers and the classifiers or the pipeline that we would like to have for a certain data set. Here in the top, I am showing you 5 different data sets. Why did we choose these data sets? This is in the benchmark of AutoML is actually the simplest available data sets. The simplest available data sets, like easy, you can get very high accuracy on that. Using the graph from IBM, this is actually leading to 0. And the 0 here, because the graph is very noisy. However, based on our own knowledge graph, the data science knowledge graph we are constructing, we are not only faster, we are also more accurate. Okay, now we are done with the graph. In order to learn, you train models. Is it easy? Okay, extract part of this graph, train models, and it's going to work. But in order of navigating this graph at the end of the day is stored as RDF graph. So in order to query the graph, you need to write a Sparkle query. And we recognize very carefully that data scientists, most of them are not aware of structured query languages like Sparkle. So for that, we are actually working with question answering system. Question answering system, I'm going to get from the data scientist or the engineer, you know, a certain query, a question in English, looking for something. Now we try to understand we do question understanding of that statement, and then, you know, generating the equivalent, semantically equivalent Sparkle query. But the thing that Essam, this is not new. There is a lot of systems, like this is a very well-defined problem. There is a lot of systems right now. Why not getting one of these systems and use it? You know, why you invent a new system here? The thing that these systems that is actually doing question answering on knowledge graph, they are working or modeled to work with a specific knowledge graph. Some of these systems, they need a huge amount of pre-processing in these knowledge graphs in order to build indices that is helping to, you know, map between what you understand from the question to the actual vertices or edges in the graph. The idea that we have, we need this system to work based on models that is trained in general, you know, generally to work with any graph. So on the fly, you can ask our system, KGCan, for question answering, to be connected with existing knowledge graph, giving us a question in English, and we start working. You know, this is the thing. Now we are relying here in decomposing the problem. Now we are relying here in decomposing this problem into 3 stages. Question understanding, and for that, we have sequence model that is trained in general about understanding or extracting triples, like named entities or entities and relation phrases. Now, the model itself just need, you know, like about 700, 800, you know, annotated questions in order to learn how to understand a question in general. And once we do that, we invented a way based on subgraph matching semantics to correlate between entities in the question and vertices in the graph. And based on that, we like for now, the system is like invented and developed to be working later with our knowledge graph, but we can also work with existing ones. Like DBpedia, there is a very well-defined benchmark called CALD9, and this is a very challenging benchmark. As you see that, for example, here, NSQA, this is a system also developed by IBM. They achieve in that benchmark, which is very challenging, a precision of 30, let's say 32, about 32, and F1 measure about 31. So you can imagine how challenging this benchmark is. You know, this is really an area where we really need more work. There is another system, and this one, by the way, was published in one of the tracks at ACL conference 2021. EdgeQA was published also last year in ESWIC. This is like an international conference in semantic web. This is like a top tier conference for people working in semantic. And it was achieving slightly better than IBM system by 32. KGCan, based on our models and techniques that is developed and trained independently of the graph, we managed to achieve very high precision comparing to them and very high, you know, F1 measure in total. We also tried with another benchmark, which is, it is much easier because it is based on template questions. The CALD9 is based on real human being questions that is collected from different logs. Because LC-Quad is working with template questions, we have actually more questions. Like the actual benchmark is tested with 1,000 questions. And for that also, we are doing much better, especially in terms of precision. We are still working to improve that, but we are slightly, you know, less comparing with EdgeQA in terms of F1 measure. But again, we have the advantage of as we see here, we directly can connect with any graph without any pre-processing. Okay, from these two applications of linked data science, our KG-led system and KG-CAN, we recognize that although knowledge graph systems was developed, based on semantics, we are using NLP techniques in order to recognize stuff. We are using data, classification models from deep learning models in order to figure out, semantics in this knowledge graph. The funny thing is that we cannot query our knowledge graph based on semantics. So we have limitations. While we are doing semantic subgraph matching for KG-CAN, we had to actually retrieve data, the nodes and edges from the graph outside to KG-CAN in order to apply the semantics. Same thing also when we work with modeling stuff for KG-LEDs, we had to do that outside the knowledge graph. We find it now a very good opportunity with this growing interest in applying deep learning on top of knowledge graph. What we are focusing in our lab is graph neural network. We found it is a very good opportunity to provide embedding as a service. This graph neural network is relying on calculating embeddings, representation learning of nodes and edges or subgraphs. So instead of doing that outside the graph engine, we do it as part of the graph engine, as part of the query optimizer of the graph engines. This is still work in progress, but we managed to have some few, we worked with different 4 cases in order to show how much we can save. The things that I would like you to look at is actually the last item, which is we can see the advantage here. If you are a data scientist, if you are a software engineer, and you would like to apply this kind of semantics on top of knowledge graph, you have to write your own code. In these different cases, you will see that it is hundreds lines of code, more than 100 lines of code. Now, using our system, it will be a simple query. And for that, it is a few lines of code, 10 lines of code, 20 roughly lines of code. And this is not the complete query, it is even the query plus some other stuff that you need to provide. So there is a huge advantage here, automating the semantic investigation of knowledge graph, but as part of the knowledge graph itself. So this is, I'm approaching here the end, and no any questions, hopefully you are flowing. But this is now what we are mainly focusing on our lab. There is some side projects, related to each of these directions, but this is the main, directions we have in our lab, working with constructing data science knowledge graph, working for question answering in order to make navigation and exploration of data science projects much easier. One of the side projects we are actually, we are still hiring more master and PhD students for working in this. We can imagine after that, we can have a complete chatbot. For example, in our collaboration with Borealis AI, we can imagine a data scientist joining Borealis AI recently, and they would like to learn more about what is going on with a certain data set or with a certain task. They can start chatting with the chatbot in order to understand what is going on. This is one of the potential application here. Plus the reduction, once we have our KGNet, the amount of code we need to write to develop our system, in KG-CAN and KG-LEDs, is going to drop dramatically because now there is an engine behind it to solve a lot of these problems. Here, I would like to thank a lot the team and who's actually really leading and working in that. KG-LEDs is actually having a 1 PhD student, 1 master student. KG-CAN, as you see that, the main directions, there is a PhD student working in the project, plus we have side projects. For example, Shubham in KG-LEDs is leading now a project with functionality applications must doing, and for that we are trying to use deep active learning in order to automate the process of annotating the datasets. Hussein is leading the work. Hello? Hussein is leading the work on KGNet, and also Yasmin, she's another graduate student, working and helping in customizing and developing things. This is like, we are like about 2 years age group. Like we started in 2019, but with COVID and this kind of stuff, most of these students, she joined my lab starting from 2021. We have been doing really good work, like at least the vision for, as you see that we call it federated data, because actually we can build this graph coming from different data sources. This is the federation coming from, and this vision was published recently in Sigmund Record in collaboration with Kavita from IBM and Katya, she's well known in knowledge graph systems. We also had 2 demos, for our system for KGNet and KGCAN. We have now a submission for VLDB for our, scalable AutoML approach that is actually defining the problem of AutoML as a graph generation problem. Out of that, we have collaboration with 2 different companies in Canada. QHash is a cybersecurity company. For them, we are customizing our work for, data discovery, but to be more specific for sensitive data. And this is actually applied for different financial institutions. We have also collaboration with Borealis AI. This is now an approved project that is working under my tax. And for that, my student Shubham is leading there. Our collaboration with IBM AI Lab in New York in actually for automating machine learning pipelines. And with that, we have really, for now, I can say, the state-of-the-art system. The vision doesn't stop here. We still have some work to be done. And this is the overall, architecture of the platform that is we are all really hope to have, in the near future. Thank you.
We thank you very much for this talk.
Thank you. Thank you.